Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to examine matter waves. Alright, so before we get to the Davisson-Germer experiment, the one you need to know, we are going to discuss sort of a fundamentally wave-like phenomenon, and I want to give you sort of a reminder of that phenomenon. That's the phenomenon of diffraction. And we're going to discuss an application we hadn't discussed at that point. At high energies, X-ray diffraction can be used to determine crystalline structures. All right, so what does this mean? Well, the structure of a crystal, all right, that is the exact geometric arrangement of the atoms in the crystal, mean that those atoms are sort of very small distances apart. Okay, but regular distances. And as it turns out, if you send a beam of X-rays, that is radiation with with their wavelength approximately the size of the distance between those atoms, you can actually produce diffraction patterns and measure from those diffraction patterns the wavelength of the diffraction and therefore the crystalline spacing. Okay, this is a lot like using the double slit experiment to determine, with a known wavelength of light, to determine the spacing of the slit. This is very similar, just in 3 dimensions, using X-rays and probing crystalline structures to begin with. And you can see this here. If light of sort of very low wavelength is sent at a crystalline structure, an object that looks kind of like this, you get a very distinct diffraction pattern. And the math of the production of that diffraction pattern is beyond this course, but you can tell that this is very similar to some of the analysis we did in diffraction in that first, and interference in the diffraction and interference units in topic 9. And take a look at this. This is very much a real pattern that is used. So you send an X-ray along here to that crystalline structure, and you can obtain that diffraction pattern. As an important side note, this process, known as X-ray crystallography, is an active area of research today, and is actually how Rosalind Franklin discovered the double helix structure of DNA. So our classic favorite double helix structure looking like this, okay, that's not a great drawing, but you get the idea, was discovered by Rosalind Franklin in the lab of Watson and Crick, who at the time took credit for her discovery, by using, so she discovered this by using X-ray crystallography and unpacking the diffraction pattern that was revealed. So, how is this related to what we've just been discussing? Well, X-ray crystallography is very, very, very similar to the Davisson-Germer electron diffraction experiment, except instead of X-rays, we're going to send electrons. And here's the fundamental setup. An electron gun, that is a whole bunch of filaments, or a hot filament that releases electrons and then has those electrons accelerated through a potential difference, is shot directly at a thin crystal structure. Those electrons scatter, that is, bounce off the crystals and bounce off at different angles, and then when they bounce off at different angles or reflect at different angles, they, as it turns out, interfere with each other. Okay? They interfere with each other. How do we know what's going on? Well, if we take a detector and we change the angle of that detector off that reflection, we see peaks in the electrons that are detected that look exactly, identically to a wave structure, okay, to a wave interference or diffraction pattern. And this is absolutely crazy. This is an example of electrons exhibiting straight up wave-like behavior. Okay, so straight wave-like behavior. And as it turns out, although this wasn't done immediately, if you do the experiment 1 electron at a time, you will still get that same pattern. And this is really, really crazy. Obvious wave pattern, obvious diffraction pattern, which we'll see in a second. Okay, so that's pretty cool, but from that pattern, you can use what's known as the Bragg equation, which you don't need to know how to use, but should be semi-familiar, to find the wavelength. So we take that wave-like pattern, it's obviously an interference pattern, and we measure the wavelength of that pattern. And finally, the real unbelievable aspect of this experiment is that, if you go ahead and measure those electrons' momentum in a process we'll talk about in a second, you measure the momentum of the electrons, you know what momentum those electrons have because of how you're accelerating them via a high potential difference. You can then run it through the de Broglie hypothesis, and you discover that the wavelength that you measure with the Bragg equation is exactly the wavelength you would predict using the de Broglie hypothesis, knowing what the momentum of those electrons are. That is absolutely crazy. That is the smoking gun, and there is now incredibly good evidence for matter waves and for what the wavelength of those matter waves would be. So very quickly, how would we do that? Well, if they reach a maximum kinetic energy EK from rest, they have done so by undergoing a potential difference, or being sent through a potential difference here. They're a given energy E times delta V, and if you recall, the relationship between the kinetic energy and the momentum is that EK is equal to P squared over 2m. That derivation is right here. If you solve for the momentum in that particular equation, that gives an expression for the momentum in terms of the mass of the electron, the charge of the electron, and the potential difference. And that allows you to know what the momentum is of the electrons that you are accelerating through your high potential difference. Okay? By knowing what your potential difference is, the mass of the electron, and the charge of the electron, you know what their momentum is. And the wavelength you calculate using the de Broglie formula and this predicted momentum, that momentum that you know the electrons are achieving, is exactly the wavelength you see in the interference pattern. And therefore, it's really astonishing result. The electrons are individually exhibiting some wave-like behavior. And the really weird part of this set of experiments is at this point in history, we now have a really good answer to the question, what would the wavelength of the matter wave be? We know this answer pretty well, and we have no clue what the answer is to this one. We don't know what this wave is in, but we have an expression for the wavelength, one that has now been verified really, really clearly in the form of the Davisson-Germer electron diffraction experiment.